In this section, we'll set the stage for understanding passkeys. Passkeys aren't a brand new technology. They're actually a variation of a passwordless protocol that has been in development over the past few years. This protocol, called FIDO2, is key to understanding how passkeys work. We'll cover the basics of FIDO2, including how it works and its typical flows. We'll also look at its security advantages and some of the challenges you might face when using it. Let's get started. Have you ever heard of FIDO2, WebAuthn, or Passkeys? Chances are you have, since they're often promoted as the next big thing in authentication. So let's dive into the protocol and its implementations to see if it's worth the hype. But first, a bit of background on FIDO2. This protocol was developed by the FIDO Alliance and W3C, organizations that lead work groups composed of industry experts. These groups discuss security features, challenges, and future developments. The specifications are open and free to use, which means if you decide to implement Passkey, which is built on FIDO2, you can expect many vendors to follow the same standards. This reduces the problems with interoperability and vendor lock-ins. The FIDO Alliance also offers a certification process with the results made public. So when you're doing due diligence on vendors, you can check if they've been formally verified. Additionally, FIDO Alliance provides free resources such as security properties, UI guidelines, and real-world deployment stories. Now let's explore how the protocol works. In Passkeys and FIDO2, there are three main components: the authenticator, client, and server, plus of course the user. The authenticator is a device that securely stores your private key and performs cryptographic functions. It could be a USB dongle, a mobile device, or even your laptop. The client is what interfaces with the user and manages communication between the authenticator and the server, typically a web browser. The server, as in any authentication system, is responsible for verifying the login attempt. It holds your public key. The authenticator communicates with the client, and the client communicates with the server. The user interacts with both the client and the authenticator. But how do they know how to talk to each other? To standardize this communication, there are two core specifications: WebAuthn, which handles the interaction between the client and the server, and CTAP, Client to Authenticator Protocol, which manages the communication between the client and the authenticator. In these specifications, you can find every call and parameter that is exchanged to complete authentication. Thanks to that, it is possible to use the same authentication method across different authenticators, clients, and servers. In simple terms, it provides interoperability and gives you more options to pick the vendor that provides the best solution for you. The protocol defines two similar operations: registration and authentication. During the registration, a key pair is generated. It's important to note that each server requires the authenticator to register a separate key pair. This means that if you want to authenticate with 3 different services, you'll need to register 3 times. For privacy and security, each key is tied to the specific service it was created for. It may seem like a usability issue, but this is actually common across many authentication methods and can be simplified using third-party federation services like login with LinkedIn or login with Google. Let's now go through a high-level registration flow. Before starting, the server needs to bind the registration to a user identity, though how this is done is left up to the platform and isn't part of the protocol. Typically, the user either creates a new account or is already authenticated. Imagine a scenario where the client is a web browser and the authenticator is a USB dongle. The user clicks a button on the website to register the authenticator. This action triggers a call to the server to get a challenge. Then the website calls the WebAuthn API in the browser, which translates this into a CTAP request and sends it to the authenticator. The user then interacts with the authenticator to allow registration. The authenticator generates a key pair, storing the private key and sending the public key back to the server. Thanks to the pre-existing session, the public key is linked with the user's identity. Importantly, the authenticator also saves the domain of the registration, for instance, delicious.com. This way, it can track which key belongs to which service. It's always easier to understand and remember the process when you see it in action. Here's a demo of the registration flow recorded on a Mac. I use the WebAuthn.io portal as the server, Chrome as the client, and a hardware token as the authenticator. You can try this setup at home. On the left side of the screen, there's a page with a username input field and buttons for registration and authentication. On the right side, I open the browser's network tab to track the server calls. The flow starts with user entering a new username and clicking the register button. The browser then steps in and shows a pop-up asking for a PIN. User enters PIN to unlock the authenticator. After the PIN is entered, the authenticator is ready to create a signature. The hardware token signals this with a blinking light. When the user presses the button on the token, it generates a signature and sends it back to the browser, which forwards it to the server. Let's break down the messages in the process. The first one, called options, is a request sent to the server to specify the configuration we want to use. In response, we get the parameters for the authenticator to create a key pair and a challenge. Next, after the authenticator generates a response, there's another call called verification. This sends the authenticator's response back to the server. In this request, you can see the public key and signature included in the attestation object. Finally, the server's response is straightforward. It just confirms whether the verification was successful with a simple flag. Let's now jump into the authentication flow. When the user wants to log in, she typically clicks a button to start the process. The browser contacts the server, requesting a challenge and configuration. This data is sent back to the browser, which translates it for the authenticator. Please note, the browser also includes the current domain. The data is sent to the authenticator, which prompts the user to unlock it. This could be as simple as pressing a button, a user presence check, or something that actually verifies the user, for example, entering a PIN or providing biometric data. Once the authenticator is unlocked, it checks for a registered key for the domain. If one exists, it generates a signature and sends it back to the browser, which forwards it to the server. The server verifies the signature, and if everything checks out, the authentication is complete. In essence, this flow boils down to a simple process. The server sends a challenge, the authenticator signs it, and the server verifies the signature. Despite the technical complexities behind the scenes, the protocol offers an elegant passwordless solution. Let's take a quick look at how authentication works with our demo. The setup is the same as in the registration process. The user begins by entering their username and clicking the Authenticate button. The browser displays a PIN prompt. Once the correct PIN is entered, the authenticator is activated and waits for the user to press the button on the device. After that, the authenticator generates a signature and sends it to the browser, which forwards it to the server. Now let's look at the calls. First, there's the options call, just like in registration. This retrieves a new challenge from the server. After the authenticator generates the signature, we see the verification call. The signature is included in the request sent to the server. The server responds with a confirmation that everything is successful. Finally, the user is logged in and redirected to the landing page. Now let's revisit the user verification step. Authenticators typically provide either PINs, biometrics, or both. But wait, PINs are a type of password and we are supposed to run a passwordless flow, right? This can be confusing, so let's clarify. The PIN or biometric is only used locally to unlock the authenticator. This means the password or biometric data never leaves the device. It's validated internally within the authenticator, and once confirmed, the authenticator is unlocked to perform cryptographic functions. You can think of it as unlocking a safe at home to access your special stamp. You use a PIN to unlock the safe, but the PIN never leaves your house. Similarly, in Passkeys and FIDO2, the PIN doesn't travel to the server. It's purely a local mechanism to unlock your private key. I think this is enough to agree that the protocol provides a passwordless solution, even though it performs local user verification that can rely on passwords. Next, let's look at how FIDO2 and Passkeys protect against phishing. Now that we know how the parties communicate, we can dive into one of its key security features, phishing resistance. To be clear, FIDO2 as well as Passkeys don't completely stop phishing attempts from happening, but they do prevent attackers from stealing a user's session, even if the user falls for a phishing attack. Let's walk through a typical phishing scenario. As we've discussed before, attackers often set up an adversary in the middle server. They buy a domain that closely resembles their target's domain. In our example, just a one-letter difference as I is replaced with L in the delicious.com domain. Then they create a legitimate TLS certificate for it. Once everything is ready, they launch a phishing campaign using misleading URLs that direct users to their server. These URLs are delivered via email, instant messaging, or other methods. When the user clicks the link, their browser is redirected to the attacker's server, which proxies traffic to the real target server. To the user, everything looks normal. They see a familiar login screen. Up to this point, the phishing attempt is the same as any other authentication method. But here's where Passkeys and FIDO2 make a difference. The user is about to use her authenticator, which she previously registered with the legitimate server, delicious.com. When the user tries to log in, the application in their browser initiates the protocol, asking the real server for a challenge and configuration. The challenge is then sent to the user's browser, which prepares it for the authenticator. A crucial step in this process is adding the domain the user is currently on to the request. In a phishing scenario, the domain added isn't the real one, it's the phishing domain. This domain is visible to the browser and gets passed along in the request to the authenticator. Here's the key point. The authenticator checks if it has any keys registered for the phishing domain. Since the authenticator was never registered to that domain, no key exists and it returns an error. This error is sent back to the server, which stops the entire authentication process. In the end, the user is not authenticated, and the attacker never captures the session because it was never created. Let's see how this mechanism works in real life. We'll reuse the setup from the previous video. Once again, the attacker is attempting to access the victim's GitHub account. However, this time the victim is protected with a passkey. First, let's see the benign authentication. Our user logs into the github.com. They select the passkeys option and the browser sends a request to the authenticator. The user then enters their PIN to unlock the authenticator. Once authentication is complete, the user is successfully logged into their account. Now let's see what happens during a phishing attempt. The attacker is using the same evil Linux server configuration and has already sent a phishing email to the victim. The victim clicks the button in the phishing email and opens the malicious page. It's important to note that the page's domain is github.cybersoup.org, not the github.com. The victim begins the passkey login process. The browser again communicates with the authenticator and prompts the user to unlock it with their PIN. However, the authenticator attempts to find a matching key for this domain. Since this phishing domain was never registered during the initial setup, an error is displayed. As a result, the attacker is unable to capture any credentials or session cookies, which means that our victim's account is safe. You might be wondering, this mechanism protects us during authentication. But what if the malicious proxy is used during the initial registration process? Good question. The protocol mitigates this as well. It is handled on the server side. When the authenticator responds during registration, it includes the domain used for the registration process. The server can verify if this domain matches its own, and since the response is cryptographically signed, the attacker can't tamper with it. If the domain doesn't match, the server will reject the registration. Now you know how passkeys and FIDO2 protect against phishing by using secure domain-specific keys. But what about other threats? Can they handle different types of attacks? Let's explore that in the next section. Passwordless authentication promises both improved security and ease of use. But what does more secure really mean in the context of FIDO2? Let's look at some of the security properties of the protocol. One of the most important features is that the private key generated during the registration process never leaves the authenticator. This is done by design, and there's no way to extract the key programmatically. While it's true that with enough time and resources, even the most secure hardware could theoretically be compromised, for most attackers, it's not worth the effort. For everyday users, this is a huge improvement over traditional methods of storing secrets. The way keys are stored varies depending on the platform, but usually involves hardware security elements, which are increasingly common in personal devices. We've learned that FIDO2 replaces passwords with cryptographic signatures using the private key, which is designed to be nearly impossible to extract. But how does this compare to passwords? Can someone brute force a signature or guess the private key? The answer is no. Cryptographic keys are much longer than typical passwords, making brute force attacks impractical. While there are theoretical ways to weaken cryptographic algorithms, they aren't a concern for everyday use. On the server side, only the public keys are stored. These keys are used just for verification, so even if attackers breach the server, the public keys are useless to them. This is a huge improvement over systems that store sensitive information like hashed passwords. Another key security feature is attestation. From the server's perspective, you can't immediately tell what kind of authenticator the user is using. It could be legitimate hardware, or it might be software that imitates an authenticator. While this can be acceptable for testing or development, production environments need to avoid insecure authenticators. There's also the risk that the authenticator's environment could be compromised. Attestation adds an extra layer of trust to authentication. Here's how it works. During manufacturing, the authenticator vendor adds a unique key to the device, kind of like a digital fingerprint. For example, they might use a secure element that can only be programmed with this key once. When the authenticator runs the registration operation, it sends not just the usual data, but also a special signature created using this key. This signature proves the device is genuine. The server checks the signature, identifies the device, and can block devices from untrusted vendors. What if an organization wants to ensure that only the authenticators they purchased and handed out can be used? There's a feature for that. By working with the vendor, the organization can buy authenticators that support enterprise attestation. This lets the server verify and accept only those specific devices, keeping the authentication process under strict control. FIDO2 is clearly a strong authentication method, so let's discuss where it stands in terms of authentication factors. Please note that passkeys differ in this point, so we will discuss them separately in the next section. Is it multi-factor authentication by default, or does it require additional measures? The answer depends on how it's implemented. At its core, a FIDO2 authenticator represents the something you have factor, as the user physically possesses a device with a non-extractable private key. However, to meet the MFA standard, which requires at least 2 distinct factors, you need to add a second layer of verification. This is where user verification comes in. By adding something you know, such as a PIN, or something you are, like a fingerprint, you can create an MFA solution with a single device. Even the strongest security doesn't mean much if the system is hard to use. So let's take a look at how FIDO2 measures up when it comes to usability. Have you ever wondered why some solutions never achieve mass adoption, while others with a similar value succeed? The answer often has little to do with technology. While many tech creators believe their solutions are flawless, users quickly discover that even if they solve a problem, the experience of using them is terrible. Maybe the user interface isn't intuitive, or the response times are too slow. Some users might struggle with unfamiliar terminology or new workflows. Inconsistent experiences across different platforms can confuse users. Or perhaps when an error occurs, there's no clear way to recover from it. These are just a few of the common pitfalls that can cause digital solutions to fail. The same applies to cybersecurity, especially in authentication. Every type of authentication introduces friction into the user experience. Our goal is to minimize that friction, making usability as seamless as possible. So how easy to use is FIDO2? Let's find out. First, let's look at support. FIDO2 and Passkeys do exceptionally well in this area. The protocol is supported across all major web browsers and operating systems. Whether you're using an iPhone or Android phone, Windows PC or Mac, and no matter if your browser is Chrome, Firefox, Edge, Safari, or another option, you can use passwordless solutions. The WebAuthn and CTAP standards we discussed earlier ensure a unified experience across these platforms. However, when it comes to the user interface, there are some variations. Even though there are official guidelines, different implementations may create slightly different user experiences, which can lead to some friction when interacting with the authentication prompts. Compared to passwords or other MFA methods, FIDO2 stands out by being passwordless, making it much easier for users. It's simple to use and offers a rare mix of better security and convenience with almost no effort needed from the user. Sounds amazing, right? A secure, straightforward, and hassle-free solution, just like the usual marketing promises from every vendor out there. But we're not here to sell you anything. Instead, let's dive into the limitations and challenges of FIDO2 technology to give you the full picture. Finding one solution that solves all authentication challenges is nearly impossible. FIDO2 is a big step forward in authentication, but there are some important things to think about before fully adopting it. First, let's talk about the most obvious requirement. To use passwordless authentication, you need an authenticator. An authenticator is a combination of hardware and software, meaning you'll need a compatible device to use it. This could be a USB dongle, a smartphone, or a PC, essentially any device that can communicate with the client. While this isn't an issue in many cases where people often have their phones with them, there are scenarios where external devices are not allowed. As we've mentioned, for FIDO2 to work as a multi-factor authentication, you need a second factor. Not all devices have biometric sensors, and not everyone is comfortable using them. That's why there's usually an option to fall back to using a PIN. Now, what happens if the device with your authenticator is lost or stolen? Ideally, the authenticator was configured with user verification, requiring a PIN or biometric input to unlock the device. But what to do next? Fortunately, from a technical perspective, revoking the authenticator is simple. You just need to delete the public key from the server database. However, for the user, recovering access is more complicated. With passwords, recovery is often straightforward. You use a verified channel, such as the user's email address, and send a link to reset the password. But if the lost authenticator was part of an MFA setup, recovery becomes more challenging. The authentication method used in recovery must maintain the same level of security as the original method. Otherwise, it becomes an easy target for attackers. So what can be done? The recovery process depends on the use case. In a workforce scenario, recovery might be handled through a help desk, with a peer or manager confirming the user's identity. Recovery could also be restricted to specific conditions, like being on an internal network or physically present. However, in the customer space, recovery is far more difficult. Scale, usability, and security pose significant challenges. In fact, the recovery problem has been a major driving force behind the development of passkeys, which we'll cover in the next section. Lost authenticator recovery is probably the most significant process that needs to be considered alongside FIDO2 authentication, but it's not the only challenge. Users can face similar issues with device migration. For example, what happens when a user gets a new phone? Can their private keys be transferred from the old device? Unfortunately, since the private key cannot be extracted, the user is forced to go through the registration process again. If a user has hundreds of accounts, this can quickly become a major problem. Although some architectural solutions like federated login can help reduce the number of registrations needed, they don't fully eliminate the need for re-registration. This is still a hurdle that organizations must address when implementing FIDO2. Luckily, this problem was solved in Passkeys, and we will discuss how in the next section. Another challenge is the setting where authentication happens. For instance, users might need to log in while offline, but being offline means there's no way to communicate with a server to create a challenge. Then there's the difficulty of cross-device and cross-platform authentication. Imagine starting the login process on a computer while using a phone as the authenticator. That's a cross-device flow. It gets even trickier if the computer runs Windows and the phone runs Android, creating a cross-platform problem. Let's also consider shared accounts. Have you ever shared credentials with a colleague while you were on vacation? Although it's a security anti-pattern, shared access is a reality in many deployments. Passwords and even weak MFA can easily accommodate this, but FIDO2 makes sharing access more difficult. Whether that's positive or negative depends on your perspective, but it's something to think about when evaluating your authentication use cases. Lastly, older technologies can pose challenges for passwordless adoption. While support for web and mobile use cases is strong, legacy systems may take time to adapt or may never implement passwordless authentication. For example, command line access or remote desktop solutions might not be immediately compatible. The good news is that privileged access tools can often resolve these cases, but it's still another factor to consider. These challenges are not exhaustive, but I hope they help guide your evaluations. Particularly in the customer space, your decisions can impact the entire business. Even in your personal life, switching to passwordless authentication might lead to some unforeseen complications. We've covered a lot in this section, so let's quickly recap. We started with an introduction to the FIDO2 protocol, how it's defined, the key players involved, and its basic flow. Then we explored its security features, focusing on its strong resistance to phishing. After that, we talked about usability and some of the challenges you might encounter when implementing FIDO2. Usability is crucial for adopting any new technology, and we've already highlighted some of the hurdles with FIDO2. We are now ready to dive into how passkeys address these obstacles.